we introduce EventPointMesh, human mesh recovery solely from event point crowds. Human mesh recovery provides a more detailed view of human behavior compared to skeletal tracking, making it highly valuable across multiple real-world applications. Moreover, robust performance under diverse lighting is crucial. For example, mixed reality applications vary in brightness, from immersive training to stage performances. Healthcare monitoring demands 24/7 reliability, while sports and injury prevention require precise motion capture under changing light. Driving support system must function in both bright and low light conditions. These examples underscore the need for mesh-based tracking that works in any lighting environments. However, the most widely used frame-based cameras have inherent challenges. To avoid motion blur, we need shorter exposure time, which becomes problematic in low-light settings. Shooting at high frame rate demands strong lighting and quickly increases data load. And even when parts of the scene aren't moving, traditional cameras capture every frame, causing inefficiency and huge data volumes. These constraints make it challenging to achieve reliable, high-fidelity mesh recovery in real-world scenarios. In response to these challenges, an event camera is a powerful alternative. Unlike traditional frame-based cameras, the event camera is a bio-inspired sensor that detects luminance changes asynchronously at each pixel, rather than capturing full frames. It outputs these changes as event in four-dimensional space, x, y, time, and polarity. Thanks to this design, event camera achieves extremely high temporal resolution and can handle both bright and dark environments with low power and memory usage. In our approach, we leverage these unique properties to enable robust human mesh recovery in diverse lighting conditions. Here, we compare existing methods with ours. Conventional approaches, such as Event HPE, rely on intensity images to initialize the mesh and compress event data into frames, potentially losing temporal detail. In contrast, our method processes raw event point crowds, preserving their high temporal resolution and removing the need for any intensity images. As shown on the right, we directly transform these point crowds into 3D meshes, making our approach more robust, especially in low-light scenarios. Here's an overview of our network architecture. We begin with the base module, which converts the raw 3D event point crowd into high-dimensional features. Next, the keypoint module estimates 2D joint positions and extract global features that capture the overall pose. Meanwhile, the anchor point module groups event points around each joint to capture local details of each body part. Finally, these global and local features are fused in the SMPL module, producing a detailed 3D human mesh. By combining both global and local information from the event data, our method achieves accurate mesh recovery without relying on intensity images. Here, we illustrate our spatial-temporal grouping approach. On the left, you can see a visualization of actual event data showing them in 2D and 3D spaces. On the right is a conceptual diagram. We use estimated 2D joint as an anchor point and cluster nearby event data based on their distance in the image plane. By focusing on the local neighborhood around each joint, we can capture finer details of human motion, which improves the accuracy of our mesh estimation. We conducted several experiments to demonstrate the effectiveness of our proposed method. The first experiment compares the mesh estimation accuracy of a conventional approach, relying on both event data and intensity images, with our approach that uses only event data. We evaluate both approaches under bright and dark conditions. For the existing dataset, MMHPSD, the data was captured solely in bright setting. On the other hand, EPMD is our own dataset recorded in both bright and dark environments. As you can see from the right figure, EPMD includes a wide variety of motions. Here are our quantitative results. On MMHPSD, our method outperforms Event HPE Vive and closely approaches the accuracy of Event HPE GT, which benefits from a ground truth initial mesh. Meanwhile, on EPMD, our approach achieves higher accuracy than competing methods, highlighting its robustness in low-light conditions. Here are the qualitative results. The blue mesh is the ground truth. Green is our method. Red and yellow are existing methods. While existing methods sometimes misestimate certain body parts, ours stays closest to the ground truth, underscoring the benefit of local feature extraction around key joints. Event HPE ZT and Event HPE Vive, which leverage optical flow estimation, degrade in dark environments due to their reliance on intensity images, whereas our event-only method remains robust. Next, we compare a frame-based method, Vive, and our event-based method, EPM, using the EPMD dataset under both light and dark conditions. As shown in the table, our approach achieves consistently lower errors across all metrics, indicating robust performance even in low-light scenarios. In contrast, Vive's accuracy declines in the dark, sometimes confusing front and back orientations, as illustrated in the qualitative results. This highlights the advantage of relying solely on event data, which remains effective despite limited visibility. Finally, we examined how different time window settings affect our event-based method. Task 1 compares the number of consecutive time windows and shows that more windows help compensate for the temporary sparsity of event data, improving accuracy. Task 2 explores different time window widths. Although narrower windows collect fewer events and slightly reduce accuracy, the methods still demonstrate robust performance overall. This flexibility highlights our approach's adaptability to various temporal sampling rates. This video shows the qualitative results for experiment 3. The blue mesh represents the ground truth. The purple mesh is our method running at 120 fps, and the green mesh is our method running at about 15 fps, which is the same as the intensity image frame rate captured by the event camera. Our approach effectively handles high-speed motion and demonstrates performance comparable to optical motion capture. Up to now, we've focused on the strengths of our proposed method. However, there are still limitations and potential future directions. Issue 1 is the lack of events when body parts remain still. An autoregressive network could handle these inactivity periods. Issue 2 occurs when the subject is partially or entirely out of view, degrading pose estimation. For this issue, bounding box detection might help. Issue 3 involves multiple entities like people, object, or shadows that can cause misdetection. Improving subject segmentation could address this issue. By tackling these challenges, we can move closer to practical real-world deployment of event-based mesh recovery. Thank you for watching.